Hello, dear students. This is part 3 of the design of T-beam bridge. In this section, we are going to design the uh, cross beams and the intermediate cross beams as well as the end cross beams. The same design we are going to continue. You can see over here the cross beams. Now the major concern is with the longitudinal section. The cross beams are placed at 3.625 meters. These are the end cross beams. All others are the intermediate cross beam, and at the end you have again a end cross beam. So we have 5 cross beams. 3 are the intermediate, and the at the ends the 2 are the end cross beams. The with a depth of 1275 mm, yeah, 1.275 meters. The section is 250 thick. You can see now the for the design. If you look at the plan, these are the longitudinal girders. So in between these we have the cross beams. So 1, 2, 3, 4, 5, and so on. So we have 5 cross beams. So the load dispersion is trapezoidal. So you can see over here. So that means a cross beam will cater one section, triangular section from here and the other one from here. So this will be the load coming on the cross beam. The total load can be calculated. The load intensity can be calculated with the help of the dead load of the this deck slab as well as the bearing course. So let's see. Then data I have given you. The spacing of the cross beam is 3.625. Effective span is 2.2 meters. Bending moment due to the dead loads. First is weight of the deck slab and the bearing course per meter square. So I've told you it is 0.215 is the thickness of the deck slab into 25 unit weight of concrete plus thickness of the bearing course into unit weight of concrete. So this gives me 7.25 kilonewton per meter square of the intensity of the load which is covered for over here. Total load on the cross beam due to this trapezoidal section will give me, so two sections of triangular section 0.5 mm. This is 2.2. So it is 2 into 1 by 2 into 2.2. This is the area of the triangle. So this is 45-degree dispersion. So this is 2.2 by 2. So into 2.2 by 2 into the load intensity 7.25 kilonewton over here. So this gives me load coming on the cross beam as 17.55 kilonewton. Then there will be self weight of the cross beam and the weight of the bearing course over the cross beam. So self weight will be, the span is 2.2, thickness of the cross beam is 2.25, and it is at a depth of 1.275 with 25 as the unit weight of concrete. For the bearing course again it is 2.2 into 0.25, thickness will be 0.075 into 25. So this gives me a load of 18.56 kilonewton. When you summarize this, it comes up to be 36.11 kilonewton as the total load. Now the cross beams are to be designed as a continuous beams. So here the coefficients will be as per the we have seen in the IS 5456 the coefficients for continuous slabs or the continuous beams. So from there the coefficient for maximum positive bending moments for the intermediate cross beams, it is 1 by 3 into 0.07 plus 2 by 3 into 0.042. These are the for the end conditions. So we get it as 0.051. This is for the coefficient for maximum positive bending moment. For negative bending moment, which is at the supports, so for support moments it is 1 by 3 is this 0.125 into plus 2 by 3 into 0.083. So this gives me 0.097. Then I can find out the positive bending moments. So it is the coefficient. So positive bending moments will be the positive bending moment coefficient 0.051 into the load into 2.2 per meter. So this gives me 4.05 positive kilonewton meter as the positive bending moment. The negative moment used as the negative bending moment coefficient, same 36.11 into 2.2 into 1 gives me bend negative. So this is the positive bending moment, this is the negative moment bending moment due to the dead loads. Similarly, I will be calculating it for the live load. Now live load disposition is something like this. Class AA tracked vehicle has been used, which is symmetrically placed over the intermediate cross beam. So you can look upon here. The 3600 is the contact area for the tracked vehicle, which consists of one track. Total load coming from tracked vehicle is 700 kilonewton. So I'll be taking it as 350 kilonewton for one track. So 350 kilonewton load is for this 33.6 meters. So I will be placing it and will be calculating for dispersion of this this area onto this cross beam. So let me see. Load on the cross beam is calculated as this is 350 divided by 3.6, that is this one will give me the load intensity from the tracked vehicle, into 1.675, that is the for the distance for which it is being disposed on the slab, into into 1.675 divided by 3.625 is the center to center distance of the cross beam, yani the span between these two cross beams. So into 2.662. 2.662 is the distance of the other cross beam from the center of CG where this load is calculating. So this is the CG. So this distance is 2.662. So this gives me for the load or from the this area on the cross beam. Then I have this load from the cross beam, so it is 350 again intensity into 0.25, which is the thickness of the cross beam. This total makes it to 263 kilonewton. So total 263 kilonewton is the load on the cross beam for if the load is placed in this fashion at the central way. Then the coefficient of maximum, again the coefficient I have been calculating, so it is 1 by 3 into 0.203 plus 2 by 3 into 1.215. This is the positive bending moment. So major is from the central, that is WL by 8. This is the coefficient is WL by 8, which we have been doing earlier also. So this coefficient combined comes up to 0.5151. For negative it comes up to be 1.146 with the 1.3 into 1.188 plus 2 by 3 into 0.125, again WL by 2. So this gives me 0.146. So positive bending moment including impact is 0.151 into 226.3 into 2.2. Here impact also has to be come into picture, so it is into 1.25. So this gives me 109 and 106 as the positive and the negative bending moments respectively. Then combining these two, the positive moments and the negative moments, so we get the positive moments as 113.05 and negative moment as 113.37 kilonewton meters. Effective depth will be 1275 minus 40. 22 mm dia bars has been used, so minus 22 single dia minus 1 dia half dia. So this gives me 1202 as the effective depth. M by sigma STJD gives me steel. You provide, now it says add to give additional stiffness to the beam. So as per the bridge code, 0.3% area has to be added. So 90. So this total area which is required, so 901, sorry, this total zero comes out to be 1423.51 mm square is the desired area. So providing 6 bars gives me a total area provided as 2281 mm square. Negative steel, on the same instance we get it as 3 bars of 22.5 mm dia, giving an area of 1140 mm square area. So this is about the steel which has to be provided. Then I have to check it for shear. For provision of shear, the loads are spaced like this. The cross beam, this tracked vehicle is placed over here on the longitudinal girder. So you can see here the this is the cross beam. So the total effect from here, so I will get the shear near the girder C. Let me check it for this instance. For this section I am going to check it for the shear force. So this shear force is given by 263 is the load coming on the cross beam, so divided by 2.2, that is the spacing, this is the span of the cross beam total 2.2. I'm checking over here, so it will be 2.2 into 2. So that means 263 divided by 2.2 into 2. Plus, then I have a section over here which is from the other load. This is 375 which is going to act on the cross beam. So that is 375. So 263 divided by the 850 will give me the intensity of the load into 0.375. So this is 263 divided by 0.85. 263 divided by 8.5, 0.85 into 0.375, and into 0.375 this will give me the total load 0.375 by 2 into the whole section into 2.2. So 2.63 divided by 0.85 gives me the intensity of the load, into 0.37 gives me the load, Then again you divide it by 2 will me gives me the half load for a distance of 0.375 to compete for 2.2, which is the span of the load. So try to understand this what I'm going to say. So this is the load which is going to come. This is not the load, this is rather the shear force. Total load has been considered. Draw a line diagram and you will be able to understand how to calculate the shear force. So this has to be increased by the impact factor, which is 25%. It gives me 311 kilonewton. So shear due to the dead load, which we have calculated as 17 kilonewton earlier on. So this gives me total shear of 328 kilonewtons. So again, you can shear stress you can take. This is force upon sigma st jd. So this gives me 1.2 Newton per mm square. To counter this, 4-legged stirrups has been provided of 10 mm dia at the rate 150 mm center to center. Also 2 bars of 22 mm dia crank bars to take care of the diagonal tensions. These have been provided. For the end cross beams, it has been told to us that the design remains same, but one thing has to be taken care of. That is, the depth of the end cross beam should be similar to the longitudinal girder for a distance of 1 meter, and thereof the depth will remain as the intermediate cross beam for the remaining portion. So this is the design of the T beam, where the portion I have discussed in this particular class is the design of the cross beams, end cross beams and the intermediate cross beams. Thank you, please.